Our topic for today is rational and irrational numbers. You can think about it as rational, sort of normal numbers, and irrational, not normal sorts of numbers. Together we call these real numbers. When we think about real numbers, what you want to think about is a number line and the idea that any number that you can conceive of is on this number line. Most of the numbers you can conceive of, pretty much every number, is on that number line somewhere. So, for example, -2. Well, -2 is right here. -1/2. -1/2 would be right there. Okay? Even decimal numbers. 0.7. 0.7 is going to be right about there. Mixed numbers. 2.5. 2.5 is going to be right about there. Okay? Real numbers, though, are made up of two kinds of numbers. The first kind is rational numbers. Rational numbers are those numbers that can in some way be expressed as a fraction. Okay, A over B. Now you may be thinking, wait a minute, 5 isn't a fraction. Well, 5 is a fraction. It can be expressed as 5 over 1. 2.5 can be expressed as a fraction, as 5 halves. Same with negative numbers. -2, that could be expressed as -2 over 1. Decimal numbers are the same. 0.7 can be expressed as a fraction, 7 over 10. Okay? Even repeating decimals can be expressed as fractions. So for example, 0.3333, 0.3 repeater can be expressed as a fraction. That would be 1/3. Now, I want to talk just briefly about that before I go on to irrational numbers. Whenever we talk about converting fractions to decimals, you probably already know how to do that. Repeating decimals are sort of the special ones. So if we had something like, for example, 0.2 repeater, and we want to convert that into a fraction, then what we have to do is we have to start this way. I'm actually going to move this down just a little bit so it's easier to work with. 0.2 repeater, and we're going to say, well, that's x. And then what we're going to do is there's one repeating decimal, so we're going to we're going to multiply by 10, which gives me 2.2 repeater. In other words, I've just multiplied it by 10. And then what I'm going to do is I'm going to subtract. So I take that away, and I do this side. 10x minus x is 9x. And on this side, the reason I multiplied by 10 is because I want to get rid of that repeating digit. And that's exactly what happens when I subtract. This goes away, and I'm left with 2. And then I just have a fairly simple algebra problem. X, divide both sides by 9, x is equal to 2 over 9. Now whenever I have two decimals that repeat, let's say for example 0.23, and both of them repeat, again, let me write that a little lower so I can deal with it more easily. 0.23 repeater. Again, I'm going to say x equals. Now, because there are two digits that repeat instead of one, I'm going to multiply by 100. Two zeros. 100 times x. And you'll see how this works. That way, I multiply by 100 and I get 23.23 repeater. And the reason I did this is because I want to get rid of the repeating part, and that's exactly what happens. When I subtract, I have 99x equals, this part cancels itself out, I'm left with 23. And again, it's a fairly simple algebra problem. I divide both sides by 99, and I get x equals 23 over 99. Sometimes these problems will need you to simplify that again, but this isn't an example of that. Now, these do get a little bit more interesting whenever I have something that repeats a little further down in the area past the decimal. So let's take this example. Let's say that x is equal to 0.23. Now you'll notice, rather than the 2 and the 3 repeating, it's only the 3. So, since I have one decimal place repeating, then I'm multiplying by 10, and I get 2 point, and this part multiplies like that. And when I subtract, I still get 9x is equal to, and when I subtract, the repeating portion goes away and I'm left with 2.1. Again, fairly simple algebra problem. Divide both sides by 9, and I get 2.1 over 9. And you're probably thinking, wait a minute, that doesn't look very clean. It's a decimal within a fraction, still have a decimal number. How do I fix that? I multiply both the top and the bottom by 10. It's just like simplifying a fraction, except I'm multiplying here. And I'm left with x is equal to 21 over 90, because I multiplied the top and the bottom by 10. And you'll see now I have a fraction that needs to be simplified, because you'll recognize both the top and the bottom divide evenly by 3. And I'm left with 7 over 30. And if you were to convert that to a decimal number, which you could do with your calculator, 7 divided by 30, or 7 over 30, you would get 0.23 repeated. Okay? So, repeating decimals like these can be converted into fractions, so they are rational numbers. What then am I talking about whenever I talk about irrational numbers? Well, irrational numbers are those numbers that don't fit quite as evenly into the fraction form. They don't fit at all into the fraction form. What are examples? Well, how about this one? Let's say we had this math problem. You've done these. I have Pythagoras. And Pythagoras gives me a triangle that is 1 here and 2 here. How do I figure out the hypotenuse? You know this. I square the 1 and I get 1 squared equals 1. Square the 2, 2 squared equals 4. I add those two together, and that means that the hypotenuse is when I square the hypotenuse, I get 5, which means that the hypotenuse itself is the square root of 5. That's an example. Well, where is the square root of 5 on our number line? Well, it's not quite 3, because 3 times 3 is 9. It's a bit more than 4, because 2 times 2 is 4. So the square root of 5 must be somewhere in here on my number line. But I don't know exactly where, because whenever I work it out, it's a decimal number that never repeats, but it also never stops. It goes on and on and on and on forever, but never repeats. How about the number that we use all the time when we're dealing with circles? Pi. Where is pi on my number line? Well, pi is a little bit more than 3, so pi is going to be about there. Right? But we can't express it as a fraction. 22 over 7 is an approximation of pi, but it's not actually pi. 3.14 is sort of like pi, but it still goes on, 3.14159, and it goes on indefinitely. It goes on forever without repeating. So those are examples of irrational numbers. There are quite a few others that are standard in mathematics, but the ones that we see the most often are what we call surds. And surds, or radicals, are numbers that have the square root sign over them. Okay? This is also called a radical. It's the square root sign, and let's say, for example, the square root of 3. That's an example of a surd. Okay? Even if we put a minus in front of it, it's still an irrational number. Okay? Examples of numbers that are not irrational numbers. Well, we already talked about fractions that become repeating decimals, like 1/3. That's a rational number, not an irrational. How about one like this, 137%? Well, we know that 137% could be made into a fraction. If we made it into a fraction, what would we get? Well, we would get 137 over 100, because percent means hundredths. Or we could make it into a mixed number, which would be 1 and 37 hundredths. That's also a rational number, not an irrational one. So, what do we do with the irrational numbers? Well, we can do a lot of different things with them. One of the things that we start with when we talk about irrational numbers is some rules that we use. And one of those rules is, I'm going to write these up here. When we're dealing with surds, which are the most common irrational numbers, we have this rule which says that the square root of x squared is equal to x. Because what's the square root of x? The square root of x is something that when you multiply it by itself gives you x. And what does squared do? Well, it multiplies that number by itself. So the square root of x squared is equal to x. For example, the square root of 4 is 2. Squared is 4. Back to where we started. Okay? Also, same idea, we could say this. The square root of x squared is also equal to x. Now there's a limitation for this. We can't have a negative number under the radical, so x does have to be greater than or equal to 0. Another rule that we can use, that we use quite frequently, is this one. The square root of xy is equal to the square root of x times the square root of y. In other words, if we have a number under the radical or under the surd that can be broken into two factors, we can separate it that way and have those two factors, the square roots of those factors, multiplied by each other. So, for example, let's try. Before I go on though, remember that neither one of these can be negative. So x has to be greater than or equal to 0, and so does y. Let's use an example of this. How about the square root of 32? Now when we're doing these, what we want to do is find the square factor. And what that means is the number that is a perfect square. These numbers that I've written down, which you may want to do when you're actually doing work in this area, if you don't have these in your head yet, 1 squared is 1, 2 squared is 2, 3 squared is 9, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and if I keep counting 36, 49, 64, 81, 100, 11 squared is 121, 12 squared is 144, if I kept going, 13 squared is 169, I could keep going further, 15 squared is 225, and so on and so forth, and we could go on forever that way. But these are the most common ones that we'll deal with. What we do is we look at something like this number, and we say, what's the biggest number over there that I can divide it evenly by? And the answer in this case would be 16. So 32 is 16 times 2. 32 is 16 times 2, so these square roots together make that one. And then we realize that the square root of 16 is 4. And this is just 4 times the square root of 2. Similarly, if we had a number like this, 3 times the square root of 200, what is the biggest perfect square that goes into that? Well, 100. 100 is 100 times 2 is 200. Then we know that the square root of 100 is 10. So we're left with 3 times 10 times the square root of 2. I left the multiplication symbols out there. And we get, when we write that down, 30 square roots of 2. Now, we can use slightly more complicated ones, but before we do that, we sometimes get problems that say, write a surd as a positive, square root of a positive integer, which is just going backwards. So if we had a number like this, 2 square roots of 5, and we want to write that as the square root of a positive integer, we realize 2 times 2 is 4, square root of 4, square root of 5 is the square root of 20. Okay? That's just going exactly backwards. The last rule we want to talk about very quickly is this one, which should make some sense to you, I hope. In other words, if we have a fraction, we can separate it and put the surds on the top and the bottom. Do a quick example of that. Square root of 75 over the square root of over 9 is equal to the square root of 75 over the square root of 9. And we know that the square root of 9 is 3. 75 is 25 times 3. Square root of 75, square root of 25. And the square root of 25, of course, is 5. Square root of 3 over 3, and that's how we use that rule. Also, please keep in mind that x and y both have to be positive. Or x has to be greater than or equal to 0, and y has to be greater than 0 because we can't divide by 0 on the bottom of a fraction. And that is rational and irrational numbers.